Hi, I'm Kai. Now I'm going to do the question 2 of homework 11 for probability and stochastic processes. Question 2, we have three functions of v. Um, Fv is equal to e to the power of minus times absolute value of v, and Fv is equal to sine v squared divided by v squared, and Fv is equal to 1 when the absolute value of v is less than or equal to alpha, and Fv is equal to 0 when the absolute value of v is greater than alpha. So we have these three functions, and these three functions may represent an autocorrelation function of a y-sense stationary stochastic processes by setting v is equal to tau, or a spectral density function by setting v is equal to omega, or both. So which function f of v may represent either or both? At first, we need to know the properties of autocorrelation function R of tau and the properties of the power spectrum S of tau. So if R of tau is an autocorrelation function of a real y-sense stationary stochastic process S of t, and we have those properties, and the first is R of tau is real and even, and the second one is R of tau is less than or equal to R of 0, and the last one is Fourier transform is non-negative. And if S of omega is a power spectrum of a y-sense stationary process of x of t, then it is non-negative. And now we have those properties, and then we can check these three functions to see if they have those properties. The first function, f of v, is equal to e of e to the power of minus absolute value of v. And first, it's easy to see that e of minus absolute value of tau is even, and R of tau is equal to e of minus absolute value of tau is less than or equal to e of minus absolute value of 0, and this is equal to R of 0. And then the Fourier transform of this function is 2 omega divided by omega squared plus omega squared, and alpha is greater than 0, so the Fourier transform is non-negative. So the function f of v can represent an autocorrelation function. And then we check the power spectrum. The power spectrum S of omega is equal to e of minus absolute value of omega, and it is greater than or equal to 0, so it is non-negative. It can represent a spectral density function. Now we check the second function f of v. It is equal to sine v squared divided by v squared. And first, the autocorrelation R of tau is equal to sine tau squared divided by tau squared, and this function is even function. And this function is less than or equal to the limit tau goes to 0 sine square of tau divided by tau, and this limit is 1. It is less than or equal to 1, and its Fourier transform is non-negative, so it can represent an autocorrelation function. And now we see the power spectrum function, and S omega is equal to sine omega squared divided by omega squared, and this function is greater than or equal to 0. So it is non-negative. It can represent a spectral density function. And the last function is f of v is equal to 1 when the absolute value is less than or equal to alpha, and it is equal to 0 when the absolute value is greater than alpha. First, we can its Fourier transform is 2 times sine omega alpha times omega divided by omega, and this function is non-negative. So we know its Fourier transform is not non-negative, so it cannot represent an autocorrelation function. And then we check the power spectrum. The S of omega, we can see its value is 1 and 0, so it is greater than or equal to 0. So it is non-negative. It can represent a power spectral function. It can represent a spectral density function.